in your first course, you have seen how to calculate stresses in components like bars, shafts subjected to axial loading, bending loading and torsional loading. These are simple situations. Most often, components in machines are having complicated geometry. They will have three-dimensional configurations like this. They are subjected to loading. Under the action of the external loading, internal forces develop. Each and every point undergo deformation, and there are also internal forces at each and every point. Our objective today is to see how these internal forces can be quantified at a point, and also how the strains can be quantified at a point on the body. In order to do that, we are interested in quantifying the stresses and strain at a point, let us say P, and what we consider, we try to enclose this point by a very small cube, and when we try to segregate this cube from the rest of the body, and I will draw it to a larger scale here. So, this point around the point P, this body is subjected to forces by the rest of the body. Each of these 6 faces of the body will be subjected to some forces, internal forces, which we can show by the forces like this. So, there will be 6 faces and 6 forces coming up on each of the faces. We can express these forces per unit area, and as the size of this cube is shrunk to 0, we will find that the stresses or force intensity at the point P will be obtained. So, we are going to see how the stresses can be obtained from these forces acting on the 6 faces of this cube. So, we will focus on looking into the stress first. So, we will see what is known as stress or traction vector. We consider again the body. Now, if we divide this body into 2 parts by splitting it along a surface, let us say that we split this body into 2 parts by considering this split. it has now got divided into two parts, 1 and 2. Typically, if we consider a point on this surface, the force applied by part 2 on part 1 at this point P, let us say, will have a typical magnitude and direction. So, we will consider that this force is equal to delta F. Now, if we just consider an area around this point, let us say this area, which will represent by delta A. Now, delta F will have components, it can be resolved into components in the three Cartesian directions x, y and z. Let us say that these components are, in the x direction is delta f x, in the y direction is delta f y, and in the z direction delta f z. Now, when you try to take the intensity of this force delta F per unit area, or when we try to calculate the intensity, that is delta F by delta A, and if delta A tends to 0, we get one limit which is indicated by S. So, therefore, this intensity of F given by this ratio, that is defined as S, and this is known as traction or stress vector. Now, we can also define limits like the following. Sx is given by delta A tending to 0, delta Fx by delta A, that is the component of the traction in the x direction. So, also we can have Sy limit delta A tending to 0, delta Fy by delta A. Similarly, Sz limit delta A tending to 0, delta Fz by delta A. So, these components Sx, Sy, Sz, they are known as traction components. Now, we will try to go into considering the stresses at a point. The body that we have considered, we will again consider the same body And now we would like to consider splitting this body into two parts by considering a plane passing through our point P, and it is perpendicular to the x axis. So, we will have our Cartesian directions as before. So, we now consider a plane which divides this body into two parts, and this is the typical point we are concentrating on, P point. Now, the outer normal to this plane, if we consider this part 1, so we will draw it separately. So, this is our part 1, and the outer normal on this plane is oriented in the positive x direction. And now, if we consider an area, very small area around this point, let us say that area is equal to delta Ax. Now, this area is delta A, but we give this suffix A to indicate that the outer normal to this area is directed in the positive x direction. Now, if you try to consider the part 2 of the body and the same plane, so this is the other part of the body. So, this is part 1, this is part 2. Now, if we consider the point P on this area and the outer normal to this area is now directed in the opposite direction. So, this point is out, the normal to this plane is now directed exactly in the opposite direction. So, therefore, if we now consider this area here on this surface, it will be also indicated at delta Ax, but we consider this area to be negative because its outer normal is directed in the negative x direction, and this area its outer normal is directed in the positive x direction, that is delta Ax, and this is positive. Now, the force which is applied by part 2 on this is going to have arbitrary orientation, and this can be resolved into 3 components. So, we draw it little to a larger scale. So, therefore, I would like to draw this again, and let us draw it to a larger scale. So, we can have the force resolved into components like delta F on the x plane in the x direction, delta F x, that is the force in the x direction, and the component in the y direction, it is x plane acting in the y direction, and the third component is delta F x z. So, these are the 3 components. Now, the other side, if I just look again into the forces on the other side, so on this point again I will have the forces which are going to be just opposite. It will be directed in the negative x direction, and this component will be delta f x y, it is again directed in the negative direction, and the z component is going to be like this, that is delta f x z. Now obviously these components are mirror reflection of these components. So in fact on the negative area, please note this point, on this negative area the forces that are going to act, they are just going to be directed in the opposite direction with respect to this area which is positive. Now we can define the limits, that if the area delta Ax tends to 0, then the intensity of this force, that is force per unit area, as delta Ax tends to 0, that is what we call it to be stress in the x direction, sigma xx. Sometime we also represent it by sigma x, and this sigma x is equal to limit delta Ax tending to 0 delta f x x divided by delta Ax. So the intensity of the stress delta intensity of the force delta f x x as delta Ax tends to 0, that gives the stress on this area at the point P in the x direction. Similarly, this delta f xy can be also considered per unit area, and as delta x tends to 0, we get one component which is represented by delta x y, and it is given by delta A x tending to 0 delta f x y divided by delta A x. So this is tau x y, and it is acting parallel to this area, so it is a shear stress. Similarly, we can consider the intensity of delta f x z per unit area, and as this area tends to 0, we get the intensity at the point P, and that gives us the shear stress tau x z delta A x tending to 0 delta f x z divided by delta A x. Obviously, the stresses on this face are going to have the same magnitude, but they are going to be directed in the opposite directions. So please note this, that on this positive face we are going to have the stresses given by these values, and the stresses on the negative face, this area, is going to be given by the same magnitude, but they are directed in the opposite directions. And note that this sigma xx is acting normal to the area, so therefore it is known as normal stress, and the other two components tau xy, tau xz, which has arisen out of delta f xy, delta f xz respectively, they are acting parallel to the area, so they are known as shear stresses. We can now consider a plane dividing the body which is perpendicular to the positive y direction. So if we consider the bottom part of this body after we have divided it by a plane perpendicular to the y direction, this is the bottom part, and now the point P, we have really consider this plane passing through the point P, and if I now consider a small area, so just I think I will redraw that. So if we consider this bottom part, this is the point P, and now we consider the area around this point. This area we would like to indicate by delta A y, y suffix indicates that the outer normal to this area is directed in the positive z direction, I am sorry, positive y direction, because this is our y axis. Now the force which is applied by the second part on the first one at this point would have again some arbitrary orientation, and it can be resolved into components like this. We will have one component which is delta f y y, then we will have one component which is parallel to the x axis, so therefore this is acting on the y phase in the x direction, so this is delta f y x, and then we are also going to get components in the z direction, so this is delta f, it is y plane z direction, so therefore this is delta f y. Now if I consider the intensity of these forces per unit area, and then as we take the area to shrunk to 0, we get the limits, we get the stresses like this, delta tau yx limit delta a y tending to 0, delta f yx by delta a y. So that gives us the shear stress acting in the x direction on this area. Similarly, if we consider the limit delta a y tending to 0, delta f y y by delta a y, that gives us the stress in the y direction, sigma y y or sigma y. Similarly, if I take the third force and if I consider again similar limit, we get the stress tau yz delta a y. So these are the three stresses acting on this plane, which is positive y plane passing through the point P. So we have got again three components of stresses acting at this point on a plane y. If we consider a plane passing through the point which is perpendicular to the z plane, so we will have again the division of the body like this, and the point P is here. If we consider again an area enclosing this point, that area will be indicated as delta A z, its outer normal is directed in the positive z direction. Now the force acted upon or force acting on this area will have components in the 3 coordinate directions. We can resolve them by the components parallel to z axis delta f z z, and the component which is parallel to the y axis is delta f z y, and the component delta f z x. So, these are the 3 components of forces which are acting at this point because of the external loading. And from these again you can calculate the 3 components of stresses, which will be represented by tau zx arising out of this force, tau zy arising out of this force, and sigma zz or sigma z arising out of this force. So, thus you can have 3 planes passing through the point, and as you calculate the intensity of these forces, internal forces, and as the area is shrunk to 0, we get the stresses at the point P. And we have seen that there are 3 planes, and on each of the planes there are 3 stresses. Therefore, we will have now 9 components which we can write at one place. Sigma x is the stress, normal stress in the x direction, tau xy is the shear stress in the y direction on the x plane, tau xz is the shear stress on the x plane in the z direction. Similarly, for the y plane we will have stresses like y plane in the x direction, then normal stress in the y direction, then shear stress on the y plane in the z direction. Similarly, for the z plane we will have tau zx, tau zy and sigma z. So, these are the 9 components. These are nothing but the components of 3D stress tensor stress tensor at the point P. If we make use of the initial notations, if we indicate the x direction by 1, y direction by 2 and z direction by 3, then in that case we can represent these stresses in the following form: sigma 11, sigma 12, sigma 13 on the plane 1, sigma 21, sigma 22, sigma 23 on the plane 2, and sigma 31, sigma 32 and sigma 33 on the plane 3. So, this is also the way that stress tensor in 3 dimensions are indicated. In fact, by using tensor notation we can indicate these stress components by simply by sigma ij, with the implicit assumption that I takes up value 1, 2, 3, so also j takes up value 1, 2, 3. Now, to indicate the stresses at a point, we try to consider, as I have said earlier, a unit cube or an infinitesimal cube, and the intensity of the forces acting on these faces are nothing but the stresses at the point. Intensity of the forces acting on the faces are nothing but the stresses at the point. Now you can see that if we are trying to say that this stress at a point is nothing but the intensity of the internal forces as the size of this cube is shrunk to 0, and now we have seen that this stresses acting on the face here is nothing but sigma x stress, and in this direction it is nothing but tau xy, and the stress in this direction is nothing but tau xz. Similarly, the stresses acting on this face, which is perpendicular to the y, is nothing but sigma y, then we have tau yx, and this is nothing but tau yz sorry, and the stress which is acting on this plane, they are again having components like sigma z, and the component in this direction is tau zx, and the component here is tau zy. So these are the components on the three positive faces, and now the components which are acting on the negative faces, that can be obtained by considering the mirror reflection of the components on the positive faces. I would like you to concentrate again on one diagram which I have shown you earlier, that the stresses on the negative face here are nothing but the mirror reflection of the stresses on this face. So therefore, they are, as the dimension of the body is shrunk to 0, the stresses on the negative face are going to be nothing but mirror reflection of the stresses on the positive faces. So we can now draw the stresses on the positive face. So if we want to show this stress on this face, it is going to be nothing but sigma x directed in the negative x direction, and shear stress is going to be tau xy, it is directed in the negative y direction, and the shear stress in the z direction is going to be directed like this. Similarly, on the negative z face, we will have the stresses given by the shear stress is going to be directed like this. It is this is going to be directed in the negative direction because it is negative z face. So therefore, this is tau zx, and we are going to have the shear stress here tau zy, and the normal stress is going to be directed like this, which is nothing but sigma z stress. And the stress at the bottom point or bottom surface, stress at the bottom surface is going to be again given by sigma y acting in the negative direction, and the shear stress, it is going to be tau y x, and the shear stress on this face is tau y z. So that's how you are going to get the stresses coming up on all the 6 faces, and under the action of these stresses the body is in equilibrium. So therefore, this is how the stresses are acting at a point in the body under external loading in 3 dimensions. So, you see that there are 9 components of stresses to define the state of stress at a point in 3 dimensions. If we consider a 2-dimensional body, which you are quite familiar, consider a thin disc like this. So, this disc is subjected to, say, external forces in its own plane. There could be loading also coming from internal points. Under the action of these forces, we will find that at a point on this body, let us say P, we will again have stresses, and we will try to show it by considering an infinitesimal square around the point, and the stresses acting on the edges of the square will be the stresses. So, therefore, if we draw to a larger scale, so this is the element around the point P, and if we select our axis to coincide with the plane of the body, then we are going to get the stresses acting on the, this is the positive x phase. So, there will be sigma x stress acting here, and there will be shear stress acting on this phase, which is x phase y direction. Similarly, the stresses on the opposite phase, which will be given by the mirror reflection. So, this is sigma x, and this is going to be the shear stress tau x y. Similarly, the stresses on this plane, which is positive y plane, which is going to be sigma y, and the shear stress is going to be tau yx, and on the negative plane it is going to be sigma y, and the shear stress is tau yx. So, these are the 4 components of stresses around this point, 4 components of stresses acting at the point P, and the 2-dimensional stress tensor is therefore indicated by these components: tau sigma x, tau xy, tau yx, sigma y. So, these are the 4 components in 2 dimensions. So, this is nothing but 2D stress tensor. Let us now consider case that the sides of this cube are of unit dimensions and the thickness. So, sides are one unit each, thickness is also 1 unit. Now, you will see that these stresses are such, this element is in equilibrium. The forces acting on this face is nothing but sigma x into 1, forces acting on this face sigma x into 1. So, they are equal, therefore, they are balancing. Similarly, this force is nothing but tau yx into 1 and this is tau yx into 1, again that is balancing. So, there is no net force in the x direction. Similarly, in the y direction, that this force is going to balance with this force. Similarly, this force is going to balance with this force. And if you now consider the moment about the point P, you will find that the distributed force sigma x, its resultant is going to pass through this point if P is at the center. Similarly, resultant of this force is going to pass through the center, so it will not produce any moment. Similarly, the resultant of sigma y and this sigma y will pass through the point P and it will not produce any moment. The moment will be produced by forces like tau xy into 1 and this tau xy into 1 and so also tau yx into 1, tau yx into 1. So, if we now consider the moment about the point P equal to, if we calculate the moment, then you will find that this moment, these two forces are of magnitude tau xy into 1 and it is acting at a distance of 1. So, therefore, moment is this, it is anti-clockwise. Similarly, the moment produced by tau yx and this tau yx is going to be nothing but tau yx and area is 1 and distance is 1. So, therefore, this is the moment and this is equal to, it must be in equilibrium, therefore, it is 0 and hence we will find that tau xy is equal to tau yx. So, this is very important that these shear stresses acting on the two perpendicular planes, they are equal. So, they are known as complementary shear stresses. So, if this is working, this has got to work and that is why this is known as complementary to this. Similarly, on this side this is complementary. So, if we extend this consideration to 3 dimensions, you will find that we will have tau yz is equal to tau zy. Similarly, tau zx is equal to tau xz. So, these shear stresses are equal and hence I would like you to look at the 3D tensor, stress tensor once again. So, we have sigma x, tau xy, tau xz, tau yx, sigma y, tau yz, tau zx, tau zy and sigma z. So, in this stress tensor, what we find that this component is equal to this component. So, they are equal in magnitude. Similarly, this component is equal in magnitude with this and this component is equal in magnitude with this one. So, all the off diagonal terms have are having similarity and this similarity gives rise to a symmetric tensor. So, the 3D stress tensor is a symmetric tensor. Now, we will like to look into the sign convention. What is a positive stress? What is a negative stress? So, therefore, we will now consider sign convention for stresses. If the stress acting on a positive phase, let us say we consider this phase, and if the stress acting on this phase, this outer normal is directed in the positive x direction. So, therefore, it is a positive phase, and if the normal stress is acting in the positive x direction, then in that case it is a positive stress. Positive phase and the stress is directed in the positive direction, it is a positive stress. Similarly, the shear stress, if it is acting on this positive area and it is directed in the positive direction, so this is tau xy, it is also a positive stress, and this is also the stress xz which is acting on the positive phase in the positive direction, directed in the positive direction, so it is a positive. So all these stresses are positive, and you will find that when the normal stress is positive, it is tensile in nature. Now, if you consider a negative phase, let us say that we will consider this component like this. Now, its outer normal, let us say that this is directed in the negative x direction, and now if the stresses are acting like this, that the stress is acting now in this direction, normal stress, this is sigma x. So, it is negative phase and it is directed in the negative x direction. Let us say this is x direction, this is y, and this is z direction. Then you see that this stress is acting in the negative direction. So, it is negative phase and negative direction of the stress. So, therefore, this stress is again positive. And suppose we have the negative phase and the shear stress which is acting here, it is tau xy, it is negative phase, but the shear stress is acting in the positive direction. So, it is a negative stress. So, therefore, this is a positive stress. So, this is positive, whereas this is negative stress. So, therefore, if area is negative, but the direction of the stress is positive, then it is negative stress. And if both are negative, if area is negative, direction of the stress is negative, then it is again a positive stress. And you will see that positive normal stress is going to be always tensile nature, it will cause tension on the area. Now, positive shear stress, I would like to give you some physical consideration for the positive stress. If you have two-dimensional problem, we can immediately consider that these are our coordinate directions. Now, the positive shear stresses, this is positive tau xy, this is also positive tau xy, and this is positive tau yx, this is positive tau yx. So, this is the positive, these are all positive stresses. Now, you will see that under the action of the stresses like these, it is quite natural to expect that the element will deform in the following manner. It will deform like this. So, herein what you find is that if you consider that this is O, this is A, this is B, OA and OB are initially at 90 degree, but because of these stresses, the angle between OA and OB becomes less than 90 degree. So, herein what we find is that the direction OA has rotated like this, direction OB has rotated like this, and therefore, this causes a reduction in the origin angle, and this is known as positive shear deformation. Positive shear deformation. In fact, positive shear stresses will give rise to the reduction in the angle in the first quadrant, and it will lead to increase in the angle in the fourth or second quadrant. Herein you see that this is positive x direction, this is negative x direction. So, this angle has increased. So, therefore, thumb rule, as a thumb rule you can take that positive shear stresses will give rise to reduction in the angle. Now, we will consider example of showing stresses So, let us consider one example of say the stress tensor at a point is given by So, these are the stresses at a point, and this is in given in terms of unit megapascal. Now, we have to show the stresses. So, show the stresses. On an element around given point. So, if we consider now the infinitesimal cube around the point, and I will just show the stresses on the positive faces, and we will have the same convention for the axis. So, these are our axes. Now, you see that on the x plane I have stress like this is 5 MPa, this is acting in the positive direction, it is 10 MPa. So, this is 10 and this is acting in the negative direction. So, therefore, it is going to be directed like this. So, this is 20 MPa. So, these are the stresses on the x plane. Similarly, here on the y plane we have normal stress is 10 acting in the positive direction, and the shear stress is acting in the positive direction. So, therefore, this is 10 and this shear stress is acting in the negative direction. So, therefore, this is going to be equal to the direction of the shear stress in the z direction. Similarly, here on this face we have the direct stress, it is in the positive z direction, which is given by 20, and the shear stress here in the x direction is in the negative direction. So, therefore, this is 20 and this shear stress is acting in the negative direction, it is of magnitude 30. So, these are the stresses as per this particular stress tensor, and you can show the stresses on the negative faces by considering the mirror reflection of this.